Welcome to today's Explainer. If you're a mechanical engineering student, a design or manufacturing engineer, or honestly, just someone eager to understand the future of our field, you are in the exact right place. Today, we're unpacking a topic that is fundamentally reshaping how we work. We're going to explore how artificial intelligence is stepping into the engineering space. And spoiler alert, it's not here to take your job. It's here to supercharge your productivity and your analytical capabilities.
To really grasp what AI means for us, we kind of have to look backward for just a second. Let's be real, mechanical engineers have always been the first in line to use new tools to boost productivity. Think about how computer-aided design software, simulation tools, and CNC machines completely revolutionized the industry. Those tools didn't replace engineers, right? They amplified what we could do. And that is exactly what you should take away from this. AI is just the next major tool in your engineering arsenal. It's here to support your workflows and give you deeper insights, but it absolutely relies on your core engineering judgment.
So here is our game plan for today. We'll start with the next engineering tool, then look at AI versus traditional automation, dive into practical engineering applications, cover ethics, safety, and verification, and wrap it all up with a lesson summary and review.
All right, Section 1, the next engineering tool. Let's see how we got here.
If we frame artificial intelligence within the historical timeline of our tools, it's really just the next logical step in a long journey of digital transformation. If we rewind to the 1960s, we see the emergence of CAD and CAM systems. Things like Ivan Sutherland's Sketchpad back in 1963 literally slashed design cycles from weeks down to hours. Then by the 1980s, automation evolved into flexible manufacturing systems. Fast forward to the 2010s, and we saw the rise of digital twins, those virtual replicas updating in real time. And that brings us to the near future. By 2026, we're looking at cognitive AI design systems. This is a whole new era where our tools don't just automate tasks, they actually learn from design history and help validate complex mechanical systems.
Moving right along to Section 2, AI versus traditional automation. It is incredibly common to hear people use the words automation and AI like they mean the exact same thing. But as engineers, we need to be precise here because they are fundamentally different. So what is AI? Well, artificial intelligence is a cognitive system. It learns from historical data, predicts outcomes, and automatically recommends optimal design alternatives. It's all about machine learning basics and data-driven decision-making. Unlike older tools, AI acts more like a co-designer. If you feed it a set of constraints and materials, generative AI can explore thousands of possible configurations and handpick the most efficient ones for you to review.
To make this crystal clear, let's put them side by side. Traditional automation, that's about fixed rules and repeating programmed tasks with very little adaptation. Think of a standard robot arm on an assembly line. It does exactly what it's told, over and over. But an AI system actually learns from data to find patterns. For instance, instead of just running a CNC machine blindly until a tool snaps, AI analyzes real-time data to predict tool wear before the failure even happens. It adapts.
All right, let's get to the really good stuff. Section 3, practical engineering applications. The tangible value of AI across our disciplines is just massive. In design engineering, generative AI helps conceptualize and optimize weight and performance. We're talking algorithms that can generate lightweight bracket designs that cut material use by 40 to 60%. That is huge. In manufacturing engineering, using machine learning-based anomaly detection can drop maintenance costs by up to 30%. And in service and maintenance, AI is driving a massive shift from old-school time-based maintenance to condition-based monitoring. Advanced AI models are hitting over 96% accuracy in industrial predictive maintenance. That means monitoring an industrial pump using real-time sensor data to predict problems, rather than just servicing it because a calendar told you to.
Now, if you want to know why this matters, just look at this staggering number, $695 million. That represents the estimated yearly cost of stalled production for large automotive plants. Factories typically lose between 5 and 20% of their manufacturing capacity just because of equipment failure and downtime. By utilizing AI for predictive maintenance, analyzing machine temperature, vibration, pressure, engineers can drastically reduce those 2 a.m. emergency failures and save a fortune.
Over in quality engineering, measurement processes are getting a major upgrade too. AI is stepping in to assist metrologists with camera-based inspections, sniffing out defects, and analyzing quality trends. It can even help with root cause analysis when things go sideways. But, and this is a big but, it still requires the engineer to properly select the correct geometrical tolerancing system in the first place. The AI is a fantastic assistant, but the foundation is still your human engineering knowledge.
Let's walk through a real industry workflow, designing a new machine component. In the traditional way, an engineer designs, analyzes, tests, and tweaks in this long manual loop. But an AI-assisted process, it looks more like this. Step 1. You, the engineer, define the requirements and constraints. Step 2. The AI acts as your co-designer, churning out optimized options. Step 3. You evaluate those alternatives using your fundamental knowledge. And Step 4. Virtual simulation and physical prototypes verify the design. The AI does the heavy lifting on all those iterations, but you are absolutely still the captain of the ship. Which brings us to Section 4, Ethics, Safety, and Verification. We all know today's hyper-competitive business climate expects innovative products on incredibly short schedules. As P. Kenneth L. Dentremont from ASME points out, an engineer's career might come to an end if an important deadline is missed. And man, that puts us in a tough spot. You've got these tight production timelines, but as a professional, you have to insist on taking the time to verify that a product is safe no matter how much pressure management applies. Even when you're using AI to speed things up, your ethical obligation to verify safety does not disappear, not even a little bit.
So what are the common traps when using AI? Well, the absolute biggest mistake is trusting AI outputs without human verification. You always have to check the calculations and safety requirements. Another pitfall is using bad data for your predictive models. I mean, if the data is incomplete or incorrect, the AI's prediction is going to be completely useless. Garbage in, garbage out, right? Also, you can't just ignore established engineering standards, like ASME codes, just because an AI thought a certain shape looked optimal. And finally, never replace human-centric risk management with fully automated decisions. Treat AI as your assistant, never the boss.
Okay, we've covered a lot. Let's bring it home with Section 5, Lesson Summary and Review.
To wrap this all up, AI is an incredibly powerful tool to improve your engineering speed, your analysis, and your decision-making. It's beautifully bridging the gap between design and manufacturing. But remember, it relies heavily on high-quality data to work right. At the end of the day, mechanical engineers have to combine AI output with deep technical fluency and fundamental engineering knowledge.
All right, let's see how much you picked up today. Question 1 of our knowledge check. What is the main purpose of AI in mechanical engineering? Think about it for a second. The answer is that its main purpose is to improve speed, analysis, and productivity by acting as an assistant. It is absolutely not there to replace your engineering judgment.
Question 2. What's the difference between traditional automation and AI? Remember the robot arm versus the CNC toolware? Traditional automation relies on fixed rules and repeating program tasks. AI actually learns from historical data, finds patterns, and helps predict outcomes.
Moving on to Question 3. What are 2 examples of AI in manufacturing? We covered quite a few great ones. 2 perfect examples from today are using AI for predicting CNC toolware and using anomaly detection to slash machine downtime and maintenance costs. Question 4. Why must engineers rigorously verify AI results? This one goes straight to the core of what it means to be an engineer. Verification is critical because you are professionally bound to prioritize public safety and stick to established codes. You literally cannot outsource ethical accountability to a software program. And last but not least, Question 5. How can AI improve equipment maintenance? Think about that shift in how we monitor things. AI analyzes real-time sensor data, like vibration and temperature, to predict problems before the equipment fails. This is what enables condition-based maintenance, getting us away from those inefficient time-based schedules. You guys did a fantastic job navigating this complex topic today. I want to leave you with one final provocative thought. As AI evolves into an autonomous co-designer by 2026, capable of running full product development cycles with really minimal input, how are you going to adapt your core engineering fundamentals to effectively collaborate with it? The future really belongs to the engineers who embrace this change while holding tight to their rigor. Thanks so much for joining me for this explainer, and keep innovating.